Hey, welcome back to your favorite calculus class. We're going to look at limits involving infinity, especially surrounding when we have some asymptotes on some rational functions and things. So we're gonna investigate the behavior of a function when the magnitude of the indivariable x becomes increasingly large, or in other words, as x approaches infinity or as x approaches negative infinity. So we're extending the concept of limit to infinite limits, okay, which shows a new term, new use of the term. So let's look at, for example, we've got y equals 3 over x minus 2. We know from pre-calc, right, where's this thing undefined at x equals 2 is where we have that vertical asymptote. So then the question is, what if we're to look at this limit as x approaches, now first of all, does it have a limit? In other words, does it agree on both sides? Well, you notice as you're approaching 2 from both sides, as you approach it from the right, you notice that we're shooting up. As we approach an x value of 2 from the left, we're shooting down, right? Values here, let me punch this into decimals, I'll show you. You know, if we were to approach 2, like let's punch in 2.5, and it spits out 6. Let's punch in like 2.1, oops, 2.1, and gives you 30, right? Shooting up. As I'm approaching 2, as I'm getting closer and closer to 2, let me pick another x value even closer than 2, 2.01. And it's way high at 300, and then 2.001. Now we're clear at 3,000. Of course, at 2, we know it's undefined. That's that vertical asymptote. So this thing, again, is shooting us up, right? It's shooting us way up. As we approach it from the left, oops. Now let's approach 2 from the left. So maybe I'll punch in 1.5, and I'm like, okay, I'm down there at -6, right? Let me pick a value a little bit closer, like 1.9. Now I'm down -30. How about even closer to 2, 1.99, because again, I can't touch 2. 1.999, right down there, -3,000. So again, as we approach 2 from the left, this thing is shooting us down, obviously. We can see that from the picture. So we know it does not get arbitrarily close to a value, right? It does not agree or get arbitrarily close to a value. We've established that before. So the limit does not exist. But we're going to try and describe this a little bit more. And we're going to say, well, what if we just looked at it as we're going from the right-hand side, as x approaches 2 from the right of this function. Now we notice, what's it doing? It's shooting us up, right? Remember how we picked like 2.5 and it gave us 6, and then we picked 2.1, we were clear up here at 30, and so on. Anyways, it keeps shooting us higher and higher and higher. So we're going to describe that now as shooting to infinity. So it has a once. There's no limit. Again, there's no limit. Limit does not exist, but we're going to describe this as an infinite limit. In other words, it shoots up to infinity. The limit as I approach 2 from the left, right? Again, as I approach 2 from the left, it's shooting us down, right? We're getting lower and lower and lower. It shoots further and further down. So the limit as I approach 2 from the left, we're going to describe that as shooting to negative infinity. Okay? That's just the table that we looked at. So these symbols, obviously infinity and negative infinity, they don't represent real numbers. They're just used to describe unbounded conditions. Remember, the limit does not exist. It's just called an infinite limit. Okay, let's do another one here. As x approaches 1 from the right and from the left for this function here. So the limit as x approaches 1 of this function, first of all, we say limit does not exist. Okay, it does not get arbitrarily close to some y value that they're agreeing on. But notice from the right, it shoots to infinity. So from the right, it shoots to infinity. From the left, it's shooting also to infinity. So since they both agree, we're going to describe that as an infinite limit, shooting to infinity, both sides. Okay, this one here, let's look at this limit as x approaches, or I'll do this in a different color here. Limit as x approaches 1. Let's do it from the right. Notice as I approach our vertical asymptote from the right, this thing's shooting down, right? So from the right, it's going to negative infinity. Again, a limit does not exist. As I approach 1 from the left, now we're shooting up, right? So shooting to infinity. So the right-hand limit goes to negative infinity, left-hand limit goes to positive infinity. Overall limit obviously does not exist at all, but they have to agree to even describe it as an infinite limit, right? Like this one here, they agree. They're both going up, so we could say the overall limit, we will describe that as positive infinity there, okay? All right, so here are a couple more. Let's look at this one surrounding at -1. So the limit as x goes to -1 of this function. Notice from the right goes positive infinity. From the left goes negative infinity. So this does not exist, the overall limit. But the one-sided limits I would describe as x goes to -1 from the right would be positive infinity. Same thing here if you're looking at 1, right? That's going to positive infinity. This is going to negative infinity. But if they did ask you the limit as x approaches 1 from the right of this function here, you'd say, sure, we'll describe that as shooting to infinity there, right? So the definition of a vertical asymptote formally means is x approaches c from the right or the left if this f of x is shooting up to infinity or negative infinity, right? So that's the formal definition. If it shoots you up or if it shoots you down, you know formally that's the definition of a vertical asymptote. Okay, so if you have a limit as x approaches c from the right or from the left, and if you get infinity, negative infinity, right, you've got a vertical asymptote. So formally, that's the definition. Now, if you remember again from pre-calc, to find the vertical asymptotes, we say, where does this thing, where is it undefined, right? So for that one, at x equals -1, f of x squared plus 1 over x squared minus 1. Now make sure you factor that. Make sure nothing cancels first, right? Top does not factor. So you say, oh, I got a vertical asymptote at x equals 1. I've got another vertical asymptote at x equals -1. So I have two vertical asymptotes, right? And one more review from pre-calc. Let's say you had a function. Okay, if you have factors that cancel, if you will, that's when you have a hole. So you have a hole there, not a vertical asymptote. So in this case, you have a hole at x equals 2, but you still have the vertical asymptote at x equals -1. Okay, because what it does is it behaves like this, but we know it's still undefined there at 2. It behaves like x minus 3 over x plus 1, but it still is undefined at x equals 2, thus the hole. Okay, now the cotangent of x, where are your vertical asymptotes on this? Well, remember this is cosine over sine, so your vertical asymptotes are wherever the sine is 0. Well, we know that the sine of 0 is 0. We know the sine of pi is 0. We know the sine of 2 pi is 0, and so on, right? And these are plus minus on all these. So x equals k pi, where k is an integer, would give you all those vertical asymptotes on that, okay? And then you can analyze your infinite limits from there. All right, so properties of infinite limits. If you have the limit as x goes to c of a function is infinity, so shoots to infinity both sides, right? So that'd be something shooting up and shooting up around c, right? And then you have a different function. It actually has a limit, right? It approaches, so for this function, whether it's defined or not, the function's L, right? It approaches, it agrees on the function, okay? So if you're taking a sum of two, where this limits infinity, if you will, this one's L, then this is kind of like thinking about infinity plus or minus L, and that makes no difference. You're just left with your infinity, okay? So if you're multiplying infinity times constant infinity, okay, if your L is negative, then it would change that. It'd be infinity times negative constant. So the product limit would shoot you to negative infinity if you were to analyze that. And finally, a constant on the top over infinity, right? This is just shooting, getting bigger, bigger, bigger. All right, so this is like, let's say the limit was 5 on the top. That was your 5. On the bottom, again, this is going infinity. So as this gets bigger and bigger and bigger, right, the overall limit, this thing is going to 0. Right? It's kind of like thinking about y equals 1 over x. If you're thinking about this limit, let me not go there. I have an example here in just a second we can talk about. Okay. All right. So limit. Here's some examples with that same thing. So the limit of as x goes to 0 of 1 is 1. Limit as x goes to 0 of 1 over x squared is infinity. So I've got 1 plus infinity. We've got infinity. Here we've got the limit at the top, so I got 2 here. I've got negative infinity here. 2 over this number shooting. This will shoot you to 0. Okay. Here we've got 3 times the cotangent of x, and this is infinity. So the limit of their products will be infinity. And finally, we've got this is 0, and this one's shooting to negative infinity. So the summation of the two will be negative infinity on those. Always best when I'm doing these, I'm gonna think about think about it visually, think about it algebraically, what's happening with values and so on, and analytically, right? Those three approaches is what you want to think about with mathematics. All right, what about horizontal asymptotes? Okay, horizontal asymptotes. So horizontal asymptote means as you go to infinity of the function, okay, so the limit as x goes to infinity of a function, in fact, let me give you that one. I was going to do 1 over x. And let's think about that for a minute. We've got limit 1 over x, here it is. Got the vertical asymptote x equals 0. Notice, as my x gets increasingly larger, right, as I pick values further and further out, I know that's not to scale, but so I plug those in. I plug in 100, I got 1 over 100, so I get 0.01 for that. I plug in 1,000, I get 0.001. I plug in 10,000, I get 0.0001, and so on. What's this thing shooting to? What's this thing approaching? It's approaching 0, right? It's getting closer and closer. The further I go out, it's getting closer and closer and closer to a y value of 0, my limit. Well, that's the definition of a horizontal asymptote. So this thing has a horizontal asymptote at y equals 0. Now, when we were in pre-calc, we gave you 3 rules. If we had a polynomial function, a to the n, x to the n, plus da da da, plus a2x squared plus a1x plus a0 over b to the m, x to the m, plus da da da, b1x plus b0. Okay. The degree is what was very telling. So the rules were, number one, if the degree of the numerator was less than the denominator, then y equals 0 is the horizontal asymptote. Number two, if they were the same degree, then we take the leading coefficients. That would end up being the horizontal asymptote. And then number three, if the degree of the top was greater than the bottom, then there's no horizontal asymptote, but if the degree of the top was one more than the bottom, we could use long division to find the oblique or the slant asymptote. And that's what we did in pre-calc, just to kind of remind you, kind of a look back there. It's kind of nice to remember those rules. So for example here, we know automatically the degree of the top is the same as the bottom, right? They're both degree 2. So the horizontal asymptote by our pre-calc rules is 5/3. In other words, if you're going to take the limit as x goes to infinity on this of 5x squared plus 8x minus 3 over 3x squared plus 2, let's think about this for a minute. As x gets really, 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 really big value, like 100 trillion, whatever it is, this makes, these right here make essentially no difference at all. And you're left with the 5/3. Now, algebraically, how you can do this, there is a process to do this algebraically. And so what you do is, if you're taking this limit as x goes to infinity, what we're going to do is we're going to divide by largest variable x to the n in denominator, and then reanalyze. And then reanalyze. Okay? So that's the x squared, right? That's the biggest one on the denominator. So what I'm going to do is I'm going to multiply the entire bottom by 1 over x squared, this entire bottom, and entire top. So each term. So what happens is, let me take each one of these. Each of them are going to be divided by x squared, top and bottom, every term here. And so this becomes limit x goes to infinity of 5 plus 8 over x minus 3 over x squared over 3 plus 2 over x squared. Now, as I let x be increasingly large, so think about, again, I'm throwing in like 100 trillion or whatever. 8 over 100 trillion, this is going to 0. Minus 3 over a huge number, again, that's going to 0. This one is going to 0. So I'm left with 5 plus 0 plus minus 0 on the top over 3 plus 0. I'm left with 5/3. So the limit as x goes to infinity of this is 5/3. So now we have an algebraic approach to do this, not just your pre-calc, right? So you divide by your largest degree. And it would be the same thing if you're going to negative infinity as well. Okay, you still get that. All right. Whoops. Well, we didn't do this problem. I'm sorry. Let me fix this. All right, so this one, 1 over 8 minus, take the limit as x goes to infinity of this function, 1 over 8 minus 5 over x squared. Now notice, as I let x get increasingly large, this piece is going to 0. So I'm just left with 1/8. Same thing if I let x go down in magnitude. In other words, negative 100 trillion or whatever you're plugging in there for x. that's going to go to 0, and you're just left with 1/8 on that. Okay. All right, let's do another one here. This is kind of an interesting one. The limit of this function as theta goes to negative infinity. Now, the cosine of theta, right? If I'm plugging in values, I'm going down a value like negative pi or negative 3 pi halves and so on. I keep plugging in values as they decrease in magnitude. Uh, your value in the numerator, right? The cosine of theta, that value is going to be anywhere from as low as -1 up to 1. So the numerator is just going to be some value between there, depending on what the infinity is. Now I know it's going down, right? I'm shooting this thing to negative infinity, but it's always bobbing between negative infinity and positive infinity, right? Because we know what the cosine looks like. It always bobs between -1 and 1. So on the top I have a constant. On the bottom, now as I plug in negative 100 trillion or whatever, right? I have some constant on the top over this, negative 300 trillion on the bottom. This thing is shooting to 0, right? That thing is shooting to 0. Right, let me give you a picture. Sine of theta, oops, what did I do here? Over 3 theta. Y equals cosine of x divided by 3x. And as I zoom out, if you notice, let me zoom in for a bit. As I go down, pops up, and then it's just going to get closer, even though it comes back and forth a little bit. The further out I get, the closer this distance is to 0. Right? See how it's closing? It's narrowing in the further I go. Here it is with some values. Maybe I plug in -1, -10, -100, 1,000, and so on. Anyways, you notice closer and closer and closer to 0 on that. And that's the point. I've got a constant on the top. This is always bobbing between -1 and 1. On the bottom, that thing is. Alright, how about this one here? Get my pen. Notice we have a rational function. I've got polynomial on the top, polynomial on the bottom. Now I know you know the rule. The rule is if the degrees are the same, I'm going to take the leading coefficient. So 2 over the leading coefficient of the x squared on the bottom, which is 1. X cubed on the bottom, which is 1. 2 over 1, y equals 2. But let's do it formally with our new way to approach these, which is look at the largest x to the n in the denominator, and we're going to divide by that. So it's x cubed, right? I'm looking at this. I'm like, that's the biggest one. Divide everything by x cubed. Everything. And then take the limit. So that I'm multiplying the top by 1 over x cubed, multiplying the bottom by 1 over x cubed. So what I have is the limit as x goes to infinity of 2 plus 7 over x cubed over 1 minus 1 over x plus 1 over x squared plus 7 over x cubed. As x goes to infinity, that goes to 0, this goes to 0, this goes to 0, that goes to 0. So I'm left with 2 over 1. Same thing as you go to negative infinity on that. Okay. Here's another one. X to the 6, so I'm going to divide everything by x to the 6, and this is, I'm taking the limit as x goes to, let's do negative infinity on this, everything by x to the 6th. X to the 6, x to the 6. So we got 10 over x plus 1 over x squared plus 31 over x to the 6. On the bottom I got 1. Limit x goes to negative infinity. This goes to 0, that goes to 0, that goes to 0. I got 0 plus 0 plus 0 all over 1. This limit is simply 0 on that. Okay? Alright, how about this one here? This will apply equally well to ratios containing non-integer or negative powers of x. So what we can do here is, I know I got a square root of all this, but we can still divide numerator and denominator by the highest power of x in the denominator. So that's that x cubed. So I can go ahead. Now it all has to still stay under the radical, but I'm multiplying the entire bottom by 1 over x cubed. So each of these by x cubed. Same thing on the top. I got to do it to the top. So there's a limit x goes to infinity of 1 over x minus 5 over x squared. This is over 1 plus 1 over x squared minus 2 over x cubed. Okay. Now as we let x increase in magnitude here, this will go to 0, that will go to 0, that will go to 0, and that will go to 0. So this ends up being 0 minus 0 over 1 plus 0 minus 0. So 0. What that thing ends up being. Okay? Now the last one, I just want to give you kind of a look at. How would you approach this one? Well, what you want to do is you want to multiply by your conjugate, top and bottom, and then reanalyze. Okay, because right now there's nothing else you can do with this. So square root of x squared plus 25 plus square root of x squared minus 1. Gotta do it to the bottom. So this is, once you FOIL this thing, right? And notice x squared minus x squared, so that's gone. So you got 25 minus 1. So we got 24. And then on the bottom we got square root of x squared plus 25 plus square root of x squared minus 1. I know what you're thinking. Well, did that really get us anywhere? Yes, we can. Now what we're going to do is we're going to divide everything by, here's my largest one, the denominator. So, but I got to multiply it by square root of 1 over x squared. So it stays underneath the radical. So this is like that, top and bottom. Okay. And this will become 24. We got, oh, I'm sorry, that's 26. Good grief. Net minus 1, that's 26. My apologies on that. 26. And then we've got down here, this becomes, this is going into these, right, because they're square roots. So in other words, that's going to be under the radical, right, like this, underneath the radical there. So I got 1 plus 25 over x squared minus, this will be a 1 right there, minus. Okay. Now I'm thinking about this, the limit. So x goes to infinity on this. Okay. And by the way, what is the square root of 1 is 1. The square root of x squared, square root of 1, square root of x squared, that's the same thing as the absolute value right there. So you could write this as 26 over the absolute value of x. And on the bottom, see how it was the limit goes to infinity. That's 0, that's 0. So we've got the square root of 1 plus 0 minus square root of 1 minus 0. And so, I'm sorry, plus right there. And so we've got, that was originally a plus. My apologies right there, that's a plus. Limit as x goes to infinity on this. So I got square root of 1 plus square root of 1. I got a 2 right there. And then the limit as x increases in magnitude, that top's going to 0. right? Because this number is getting so big, so much bigger than the 26. So I got 0 over 1 plus 1, 2. I got 0 on that thing. Okay. Thank you so much for listening. That's our introduction to infinite limits. See you guys next time.